Okay, pop quiz. What's a computer really good at?
Math, right? That's what we've always been told.
Exactly. But today's deep dive might just flip that idea on its head a little bit. We're going to explore whether large language models can actually reason,
Hmm.
especially when it comes to math problems. And trust me, it's way more complicated than you might think.
Yeah, you see, we often just assume that computers are these math whizzes.
Mm.
But with LLMs, it's not just about number crunching. It's about understanding the logic behind a problem and
Hmm.
being able to apply that logic in different situations.
And that's where this fascinating research paper from Apple comes in. They put LLMs to the test using this benchmark called GSM-8K, which is basically a collection of thousands of grade school math word problems.
Hmm.
Think back to elementary
Oh,
school, that
yes.
kind of stuff.
Yep, addition, subtraction, all that good stuff.
Exactly. But here's the catch. They discovered some limitations with GSM-8K. First, it's a static data set, meaning it doesn't change. And second, there's this risk of data contamination.
Hmm.
Imagine you're studying for a test and you accidentally see some of the actual questions beforehand.
Uh-oh.
Your score might be higher, but it wouldn't necessarily reflect your true understanding.
Right, it'd be like cheating a little bit.
Yeah, kinda.
Yeah.
And that's exactly the problem with potential data contamination. Parts of the test set might have unintentionally ended up in the training data for some of these LLMs.
Oh, so they've already seen the questions.
Yeah, potentially. Which could skew the results. So to address these limitations and to really shake things up, the researchers created a modified benchmark called GSM-Symbolic.
Ooh, okay. What'd they do?
Think of it like Mad Libs for math problems.
I love Mad Libs.
Me too. GSM-Symbolic uses templates to generate variations of the same problem. So let's say you have a problem about buying apples and oranges. The template might look like this. The template might look like this. Name buys number fruit. The template might look like this. They also buy number fruit. The template might look like this. How many fruit did they buy in total?
Okay, I see. So you could plug in like, Sarah buys 5 apples. She also buys 3 oranges. How many fruit did she buy in total?
Exactly. You can plug in different names, numbers, and fruits to create tons of versions of the same problem, but the underlying math stays the same. It's a brilliant way to see if these LLMs are truly understanding the problem or just recognizing patterns.
So they gave these LLMs the same problem, but dressed up in different outfits, basically.
Exactly. Did they ace the test no matter what?
Well, the results were actually pretty surprising. The LLMs did not perform consistently on GSM Symbolic. In fact, their accuracy scores varied a lot depending on the specific variation of the problem.
Hold on, let me check my notes. Wow, yeah, some models had massive swings in accuracy. For example, Gemma 29B had a 12% swing, and Phi 3.5 Mini had a 15% swing. That's huge.
Yeah, that's a big difference.
Hmm.
Imagine taking a math test and getting a completely different grade just because the teacher changed the names of the word problems.
Right.
That's not true understanding. It's more like fragile pattern matching.
Fragile pattern matching. Okay, break that down for me.
It suggests that LLMs might be good at recognizing patterns in the data they were trained on, but they struggle when those patterns are presented in slightly different ways. They're fixated on those surface details instead of the underlying concept. It's like recognizing a cat in a photo, but not being able to tell it's still a cat if it's a drawing or a statue.
So they're focusing on the superficial stuff instead of the core logic of the math problem. But the researchers didn't stop there, did they? They decided to make these problems even harder.
Oh yeah, they wanted to see just how fragile this reasoning really was.
So how did they crank up the difficulty?
They introduced variations called GSM-M1, GSM-P1, and GSM-P2, which involve adding or removing information to make the problem more complex.
Okay, so more information to process, more things to think about. Did the LLMs rise to the challenge?
Not exactly. As you might expect, performance went down as the problems got harder. But here's what's really interesting. The variance between the results got even bigger.
So not only were they getting more answers wrong, but their accuracy was all over the place. It's like those scientists in a horror movie who keep pushing the experiment further, even though everything's pointing to disaster.
Haha. I like that analogy.
Thanks.
But hold on tight because the researchers had one more trick up their sleeve, something called GSM-Noop. And this one was designed to really trip these LLMs up.
GSM noob. Okay, that sounds ominous. What did they do? Start throwing calculus problems at them?
Not quite calculus, but they added these tricky clauses to the problems that seemed relevant, but didn't actually change the math needed to solve them. It's like someone trying to distract you with unnecessary details while you're trying to focus.
Ooh, can you give me an example of one of these sneaky new OPE clauses?
Absolutely. Imagine a problem about someone picking fruit. They pick a certain number of apples on Monday, a different number on Tuesday, and then on Wednesday they pick double the amount from Monday. The new op clause might say something like, but some of the apples picked on Wednesday were smaller than average.
Ah, I see. It's like a word problem trying to throw you off with irrelevant information. So how did the LLMs handle this curveball? Were they able to filter out the noise and still get the right answer?
You're about to find out.
Ooh, a cliffhanger. Guess we'll have to wait for part 2 to hear the dramatic conclusion.
You won't want to miss it. Let's just say those new up clauses really threw the LLMs for a loop.
So they weren't able to just ignore that extra information.
Nope. A lot of them fell right into the trap. They tried to incorporate those irrelevant details into their calculations, which led to some pretty wild answers.
Can you give me an example? Like, how exactly did they mess up?
Remember that example with the different size apples? Well, some LLMs actually tried to subtract the number of smaller apples, even though it had nothing to do with the total amount picked.
Oh, wow. It's like they were so focused on, like, turning the words into a math equation that they totally missed the point of the problem.
Yeah, exactly.
Almost funny, in a head-scratching kind of way.
It really highlights the limitations of their so-called reasoning, and the results were pretty dramatic. Across the board, we saw this significant drop in performance. When those new op clauses were introduced, some models like the Phi-3 Mini experienced a drop of over 65%.
65%, yikes. That's a failing grade for sure. But were there any LLMs that managed to, like, see through those sneaky clauses and keep their performance up?
There were a few that did a bit better than others, but even the most capable models showed signs of struggle. It suggests that this isn't just a matter of needing more practice or seeing more examples. There's something more fundamental going on here about how they're approaching these tasks.
Okay, so if it's not just about practice, what do the researchers think is going on? Why are these LLMs, even the really powerful ones, so easily tricked by irrelevant information?
That's the million-dollar question, right?
Yeah.
The researchers believe it comes down to the difference between pattern matching and true understanding. During training, these LLMs were likely exposed to examples where all the information provided was crucial for solving the problem. So they learned to take all the details, turn them into operations, and spit out an answer. They weren't really taught to figure out what's important and what's not.
So it's like those students who just memorize formulas without actually understanding the concepts.
Yeah.
They can plug in the numbers and get the right answer sometimes, but throw in a curveball and they're totally lost.
Exactly. And that's why these no-blow problems are so revealing. They expose the LLM's reliance on these superficial patterns, rather than like a deeper comprehension of the math. But the researchers didn't stop there. They wanted to see if they could nudge the LLMs in the right direction.
So they tried to, like, give these LLMs a little extra help, like a tutor for their math problems.
Haha, you could say that. They experimented with giving the LLMs more shots, meaning more examples to learn from. They tried two approaches, one with 8 similar problems containing new-op clauses, and another with 8 different problems. But all of them had those tricky new-op elements.
So they were basically trying to show the LLMs, like, hey, look, sometimes there's extra stuff in these problems that you don't need to worry about. Did it work? Did they see any improvement with this extra coaching?
Well, the results were mixed. For some models like the Llama 3.8b, the performance stayed pretty much the same, even with the extra examples.
So even with all that hand-holding, they still couldn't shake the habit of getting bogged down in those irrelevant details. It's like they were saying, thanks for the tip, but I'm going to keep doing it my way.
Haha, that's a great way to put it. However, there was a glimmer of hope. Some models, while not the top performers overall, actually did better on the new-op problems when given those extra examples with similar new-op clauses.
Interesting. So those models were starting to pick up on the pattern of ignoring certain types of information.
Right.
But what about, like, the real high achievers, those top performing LLMs? Did any of them manage to shine through?
There were 2 models, O1 Mini and O1 Preview. That stood out in terms of their overall performance on GSM-Symbolic. They were generally more accurate and less prone to those wild swings in scores. But
there's always a but, isn't there? What's the catch with these seemingly super smart LLMs?
well, even these impressive models had their Achilles heel. While O1 Preview was incredibly robust to changes in difficulty, meaning it could handle those added or removed clauses without flinching. Both O1 Preview and O1 Mini still struggled when faced with those new op-style problems.
So even the valedictorians of the LLM class can be fooled by a bit of irrelevant information. What does that tell us about the state of reasoning in these models?
It paints a fascinating picture. To really understand why this is so significant, we need to dive a little deeper into those specific examples with O1 Mini and O1 Preview. That's where the real insights lie.
Well, then lead the way. Let's examine those examples and see what they reveal about the limits of LLM reasoning. I'm ready to get to the bottom of this mathematical mystery. All right, we're back. Ready to uncover this mystery of O1 Mini and O1 Preview. They seem like they were crushing it. What went wrong?
Remember those sneaky new op clauses? The ones that sound important but don't actually affect the math. Well, even O1 Preview, which handle the more complex problems with ease, couldn't resist those distracting details.
Okay, give me an example. Paint me a picture of one of these top-performing LLMs falling into the trap.
All right, so imagine a problem about buying school supplies. You've got prices for erasers, notebooks, and paper. Simple enough, right?
Yeah.
But then the problem throws in a curveball. It says something like, assuming that due to inflation prices were 10% cheaper last year.
Ah, I see where this is going. The question wants to know the current cost, but that little detail about inflation makes you want to factor in last year's prices, too.
Exactly. And that's precisely what O1 Preview did. It diligently calculated the prices after that 10% reduction, even though it wasn't relevant to the actual question.
So even though it's one of the most capable LLMs out there, it still got tripped up by that irrelevant information. So
Yeah.
it was so eager to show off its math skills that it missed the forest for the trees.
It really highlights this challenge of teaching these models true understanding, rather than just sophisticated pattern recognition. You know, they're incredibly good at following steps and applying formulas. But when it comes to discerning relevance in a complex situation, they can still stumble.
And what about O1 Mini? Did it fall into the same trap?
O1 Mini actually made a similar mistake. On a problem about buying sourdough bread and muffins, the problem asked how much more the bread cost than the muffins. But it threw in a detail about donating some of the items.
So the real question is about the price difference, not the amount left after the donation. Did O1 Mini manage to ignore that extra detail?
Unfortunately, no. It carefully calculated the value of the donated items, subtracted from the total cost, and then figured out the price difference. Again, a classic example of following the steps without grasping the true meaning of the problem.
So where does this leave us? We've seen that even the most advanced LLMs can be fooled by changes in how problems are presented, by increased complexity, and by irrelevant information. Are we any closer to understanding if they can actually reason?
That's the big question, isn't it? I think this research shows us that we need to be cautious about claims of true reasoning in LLMs. They're powerful tools, capable of amazing things, but they still think very differently from humans.
It's almost like we're asking the wrong questions. Maybe instead of trying to figure out if LLMs can reason like humans, we should be exploring how their unique abilities can work with our own strengths.
I think that's a brilliant insight. We need to focus on understanding both the strengths and the limitations of these models so we can use them effectively and responsibly.
So for our listeners who are captivated by the world of LLMs and AI, what's the main takeaway from this deep dive? What should they keep in mind as this field keeps advancing at lightning speed?
I'd say the most important thing is to stay critical. Don't just accept claims about what LLMs can do at face value. Dig deeper, ask questions, and pay attention to how these models are being evaluated. The more we understand about how they work, the better equipped we'll be to use their power for good.
Well said. This field is evolving so rapidly, and it's crucial for all of us to stay informed and engaged. Who knows? Maybe someday we'll have LLMs that can truly reason, understand, and even solve those tricky word problems without getting distracted by irrelevant details. Until then, keep learning, keep questioning, and keep listening to The Deep Dive.
It's always a pleasure. Until next time, LLM.